Okay, good morning, everyone. My name is Ivan Ganchev. I'm a Deputy Director of the Telecommunication Research Center at University of Limerick, Ireland. Currently on a career break in University of Plovdiv, Bulgaria, and also in Institute of Mathematics and Informatics, Bulgarian Academy of Sciences. And I'm going to present you the plenary talk, Integrated Modeling and Simulation in Internet of Things platforms. Um, this is a result of a joint international project we are carrying on with our partners in China from North China University of Science and Technology. The leader there is Professor Zhang Ji. How to go to the next slide? Perfect. Okay, so here is the outline of my presentation. First, I'm going to give you a short introduction in the area of the Internet of Things, just in case you're not familiar with this. Then a little bit about the IoT platforms, the current horizontal trends, then the need for integrated modeling and simulation in these platforms, um, and then considering an example based on our own IoT platform named Emulsion, and finally the conclusions. So the Internet of Things is a hot topic. It's one of the main drivers of the global economy already. It's a multi-service, a multi-technology area. So basically this is about using um, electronic devices spread all over the world, which are able to detect changes in the physical world and send this to a system which is able to process the collected data and send back corresponding commands to impose other changes in this world. So there are many domains in this area, like smart homes, smart cities, smart transportation, smart healthcare, smart grids, smart farming, smart logistics, and smart industries. This is the so-called industrial Internet of Things, IoT. Um, so basically, this is based on the idea of sensors, multiple sensors, electronic gadgets, which have ubiquitous connectivity capabilities, uh, collecting and sending data about changes in the physical world towards the infrastructure, uh, which is able to ingest, transform, filter, and enrich this data, curate it further if needed, in order mainly to predict the, uh, in short term, the next phase in the development of this physical world, in order to be able to influence these changes the way we need it. So to solve different problems related to human lives, to industry. So basically, using systems like this, uh, we are able to generate options, analyze these options, select the best option at this particular moment, then try to implement it in the physical world, then evaluate this implementation, and then again, if there are other problems or the problem is not solved, going into next circle and so on and so on until we reach indeed the optimal solution. So there are three main parts in the IoT ecosystem. The things itself, these are the sensors, monitoring station, trackers, etc. for detecting the changes in the physical world. And the other group are actuators, controllers, and guards for imposing these other changes in the world. The second part is the ubiquitous connectivity. So basically, each electronic gadget today has some form of communication which could be utilized in systems like this to send data in both directions. And the third part are the services, which are usually cloud-based ones. I know this brings a lot of benefits for the consumers, like saving time and money and bringing personal convenience, and also for businesses, mainly reducing the cost and continuity risk and increasing the profit and customer impact. IoT sector is growing all the time. There are different forecasts, but more or less the average forecasting is that by 2025, the value generated by the IoT technology will reach 6 trillion US dollars, and by 2030, there will be 125 billion IoT devices deployed worldwide, maybe more. So the main components of IoT systems, in addition to things, IoT devices, and the cloud, where the main processing of data is performed, include also communication gateways, which are supporting different types of communication protocols because each of these IoT devices may operate using one particular communication standards, and the other device next to it may use quite different communication standards. So they're also by communication gateway positioned nearby, which is able to establish secure and reliable communication, which with each device in its own service area, and also it's able to aggregate the collected data, even to do some pre-processing of data, like in the edge technology or fog technology, and then to send this more or less processed data towards the cloud, where the main processing is going on, and then based on this data, using machine learning techniques or artificial intelligence techniques, big data analytics is performed in order to um, obtain knowledge from this data, to discover some patterns for future development or some useful insights, which are sent as recommendations to consumers through respective user interfaces or are provided as part of the IoT services. So for a system to be able to provide IoT services, what is needed is to build the system on an established IoT platform. And currently, the main four types of the IoT platforms could be distinguished. On the top, you can see the e-government related ones. This in relation to smart city domain, IoT domain mostly. Then enterprise-based platforms in the industrial IoT domain, company-based platforms. These are for service-oriented, service-providing companies of different types, and pure business-oriented in the bottom. These are the so-called IoT verticals, which currently exist as silos, IoT silos, causing a lot of fragmentation in the IoT sector. So this includes smart water, for example, smart grids, smart utilities, smart transportation, smart production, and so forth. Independent of the type of the platform, each of these use a variety of foundation enablers, infrastructural components, existing technologies of different kinds, essential to provide essential features to the relevant consumers through corresponding applications, software applications, which are predominantly today of a vertical type, meaning they are working only with one single IoT domain, not in two or more. So the current trend in the development of these platforms is to spread over the coverage to more IoT domains, and this way to uh, achieve uh, interoperation and universality. So what is the situation with modeling and simulation tools in the existing platform? Some of these include such tools and features which allow their users to design, configure, and simulate IoT deployments, to create virtual representation of devices, sensors, communication protocols, systems, multi-systems. Some other platforms integrate third-party or in-house simulation engines supporting specific modeling languages or standards, which allow users to define behavior and interactions of virtual devices and systems. But what is needed is really is to have integrated modeling and simulation, because this will provide many beneficials in several ways. Um, Mainly allowing to identify and resolve potential issues or bottlenecks in the IoT deployment early on, and to reduce the costs and risks associated with physical implementation, and also to enable optimization of the system configuration and resource allocations, and to achieve more efficient service delivery. Uh, Next in this direction is to do this with digital twinning. Uh, as you know, probably digital twins, these are virtual models replicating the behavior of existing or a potential real-world object, system, or multi-system. Uh, these are virtual representation of such objects or systems, which are updated from real-time data and use simulation, machine learning, and reasoning to help decision making, etc. This is seen as the next phase of the digital shadow, as you can see here, where we built a digital model of a physical object or a system, but the data flow is one way, only from the physical object to the digital one, where in the digital twin, it is a two-way communication. The flow of data is in both direction, which allows to improve the model in real time based on the behavior of the physical object or system, and also vice versa to improve the operation, the functionality of the physical entity based on the insights gathered from the digital modeling. The digital twins, the current state of development could be represented in a 3D space, where here you can see on the x-axis we have the six life cycle phases of digital twins, including designing, building, operating, maintaining, optimizing, and decommissioning. On the y-axis, we have the different hierarchical levels with respect to what the digital twin is applied to. So this could be data, information, components, a single product, a single system, or multi-system. And on the z-axis, you see the 7 most common use cases today, including digitalization, visualization, simulation, emulation, extraction, orchestration, and prediction. So at the moment, different clusters could be identified. Here are the 6 main clusters developed well so far. And as you can see, most of them are on the system level, which means digital twin is applying to our entire system, including visualization, simulation, prediction, and system maintenance. Here you can see the seven most common use cases of using the digital twin technology, starting with a simple digitization of data. So any information about physical world in the digitized form. The second one is visualization, including basic digital representation of a physical object. Next is simulation, building a simulation model of a physical entity in its environment. The fourth one is emulation, building a corresponding model with real software. Extraction model of real-time data streams, mostly physical to virtual, but also vice versa. Orchestration, building a model for virtual control and updating of physical devices and systems. And the seventh one is prediction, which is actually the main one applied in the IoT area, building a prediction model to really to predict the future. It's a short-term future, of course. Okay, in the digital twins ecosystem, the main vendors could be split in two groups. The first one, which is the most influential, are the cloud hyperscalers, including Microsoft, Amazon, Google, Alibaba, etc., and the others. Companies, vendors which specialize in particular industrial sector like IBM, Oracle, Bosch, Emerson's, Siemens, and so forth. Uh, so for the integrated modeling simulation with digital twins, what this really means, these are capabilities enabling the application of simulation to the digital twin model, whereby simulation is the application of mathematical models on top of the digital twin model to analyze the systems or objects much more easily. For instance, providing basic and advanced simulation capabilities and analyzing the effects of statistical variations on the system or object performance. And the main use cases are, as I said already, predictive maintenance, achieving sustainability, and system performance optimization. So next I'm going to present uh, ideas about this based on our own IoT platform, Emulsion, which is of the new horizontal time, meaning it can provide services in different IoT domains, not just one. It's having a heterogeneous multi-service structure, which is flexible and could be easily expanded. It's a cloud-based and inexpensive, so mostly targeting the SMEs needs. Uh, of course, it has all the usual suspects, tiers. It's built of a sensor and actuator tier where we have all the sensors collecting data about the physical world and sending this through the communication tier by use of data remote transfer units of different kinds supporting different communication protocols like cellular, LoRaWAN, Wi-Fi, Bluetooth Low Energy, and so forth, uh, to a communication gateways, which are really intelligent gateways because in addition to supporting different heterogeneous communication protocols, they provide also the needed end-to-end security to the cloud and also can do initial processing of data, mainly in terms of data aggregation, and then sending this aggregated data in the cloud where the main processing is performed in order to change the existing services or provide completely new IoT services to consumers in the form of web or mobile applications. In addition, it has also, as other platforms, a middleware tier which serves as a glue uh, between all other tiers. And in addition, we have this integrated modeling and simulation tier, for the main purposes of modeling cyber, physical, and social objects and IoT services along with their characteristics, and additionally also to simulate the actual provision of IT services in order to determine the optimal structure and configuration of the system which is built on top of this platform. So this is achieved by performing different optimization tasks, and I'm going to present you shortly three types of this. The first two are in relation to the optimal deployment of sensors and communication gateways in a particular area of interest, and the third one is with respect to optimal configuration of the cloud tier. So our platform, one of the IoT domains which it operates in is the smart environment control and protection, mainly in relation to controlling the quality of the air based on the so-called air quality index, which is an American-based system with different levels of AQI index, coloring in different colors and showing whether the air in the area is good enough for breathing or not. So must be aware. So the idea here in the first optimization task is to cover a particular area of interest with monitoring stations, AQI monitoring stations, like some examples of this you can see here. This includes commercial stations, which are very expensive, actually, because they must comply to the existing standards, but also we are building our own with mainly by our Chinese partners. This could be stationary, so fixed stations, could be also mobile, which means installed on the vehicles in order to measure the air quality in particular points of interest. And here you can see a snapshot of the system where you can see what is coming as data from this station. So red color means the quality is not good. Yellows also, green is very good. So the idea is to cover the area of interest, not to have black spots like this, uh, and also to cover particular routes through which consumers are walking or driving in order to avoid polluted areas that may cause danger to their health, because different people have different health problems, etc. So in the area of interest, the thing is to cover it with the minimum number of monitoring stations in so-called geo-grid configuration without having white or black spots. But now taking into account that people usually follow the existing roads or tracks for movement, uh, using this track, the first optimization here is to position these stations in such a way that they are located on the roads, on either roads and tracks, not far away from each other, so the entire area could be reliably covered and to receive data in real time. Of course, if some of the station is malfunctioning at the moment or is going through some updating or administration, etc., so it's powered down, for example, then mobile monitoring stations come into place, so we can send vehicles for temporal collection of data in that point, so not to miss any important part of the picture. The second optimization task is in relation to communication gateways. This again, the number of these should be minimized, of course, to achieve efficient system operation. The example here is a non-cellular one, which means the stations are deployed in rural area where there is no or very bad cellular coverage. So there is no 3G, no 2G even, not speaking about 5G. So then you can rely on other technologies like LoRaWAN is one of these technologies where you set up communication gateways. These are the big points here, which can cover up to 15 kilometers in radius, so 30 kilometers in diameter. So with five of these, you can cover area of 5,000 square kilometers easily. And then um, the monitoring stations in the service area of this, of course, are served by the communication gateway. If they in the intersection of two gateways, one of these is set up as the primary one, and the other or others they set as secondary one, and this is made for reliability because if the main gateway is going down, then the secondary gateways take the load. So in the solution here, what is targeted is to achieve uniform loading on each communication gateway. So in this simple example, which gateway is serving 7 monitoring stations, so equal load among all these 5 communication gateways. But now the next optimization could be in relation to the maintenance and reducing the transport expenses uh, related to the cost of transportation of serving people. So in this case, it really makes sense to have the gateway located nearby or at the same point as a monitoring station, so to be able to serve both of them at the same time. So in this case, at the bottom of this figure, you can see the 3 communication gateways, uh, green, blue, and purple are shifted, their position is shifted to the nearby monitoring station. The same could be done actually on the top two. They can move this one to this and this to this point, maybe also shifting this monitoring station here. So this is solved, of course, automatically using corresponding software. Also, the surface area should be taken in place because wireless communication, if it's a flat area, then indeed the coverage is 15 kilometers, but if you have hills or radius shadow in some cases, in some particular parts, then the area is shrinking. Okay, and the third example of optimization is in relation to achieving optimal configuration of the cloud tier. The cloud tier, just to remind you, this is the main tier where the main processing of data coming from the sensor and actuator tier is performed. So you should take into account here that in a single IoT cluster, up to 1 million IoT sensors or devices may operate simultaneously, which means sending data at the same time towards the cloud tier. So it's a big data, really. We have different data streams coming through different servers towards the cloud. And our implementation is based on Kafka Bolts technology and Storm supervisors, which actually distribute the load among themselves. So now the question is, what is the optimal number of these supervisors? How many of them we need in this particular case with this number of sensors sending data each 5 minutes or 10 minutes or 1 hour or 2 hours, depending on the need, and how many of both we need. So again, by using this tier, we can do simulations, and you can see examples of this, results of this shown on this slide. So you can see here that in this particular case, uh, these were 10 million messages, I think, sent from the sensor tier towards the cloud. You see the optimal configuration, which means the best performance is achieved here on this point with 3 bolts and 3 supervisors. All others are suboptimal or not optimal. So here are the conclusions. Uh, this talk was focused on introducing this novel architectural element for IoT platforms in the form of integrated modeling and simulation tier. and the utilization of such tier uh, as shown would allow to perform different optimization tasks in order to obtain optimal system configuration in each particular use case and application scenario. And this is all to achieve efficient provision of services and best quality of experience to consumers. This was demonstrated on Emulsion, our own IoT platform, and the work is going on. Our next step of this work is targeting the elaboration of effective models of advanced IoT services for utilization by the modeling and simulation tier of Emulsion. Thank you very much for your attention. If you have any questions of any kind, I will be very happy to answer them. Thank you.